Welcome to our little session today. We are going to be going over thermochemistry. Thermochemistry is focused about thermodynamics, basically the transfer of heat and the transfer of energy. And in the transfer of energy, there are two basic ways that it can be transferred that we really kind of pay attention to. One is heat, and the other is work. So the change in internal energy of the system, so E is internal energy, and delta always means change. So this is the change in internal energy of the system. Okay. So the change in internal energy of the system is equal to Q plus W. Now Q refers to the heat transfer. Not the heat itself, but the heat transfer. The heat transfer of the system. Can't spell today. Okay, the heat transfer of the system. And the W refers to the energy transfer of the system through work. I'm writing like a third grader today, I don't know why. Alright, energy transfer of the system through work. Okay, so this can either be work done by the system or work done on the system. And this work that it's referring to here is usually what's referred to as pressure volume work. It doesn't necessarily have to be explicitly pressure volume work, but the only cases we're going to be dealing with are pressure volume work. So now, Q and W can both be either positive or negative. If Q is positive, that means the system absorbs heat. So a positive Q means the system absorbs heat. Okay. A negative Q means that the system releases heat. It loses heat, it releases it. And before I go any further, I really should explain what I mean by the system. Because the system is effectively any isolated group of things that I want to consider. For me to really measure any of these things, I have to have what is known as a closed system. Or at least a system where I can easily measure what is going into and out of the system, especially in terms of heat. So there are always, you can think of it this way, the universe is divided. So the universe, the entire universe in which we live, in chemistry, we like to divide the system. We like to divide the universe into two things: the system, and this is the part of the universe that we're looking at, the part of the universe that we care about, where the chemical reaction is happening. We're looking at what's going on, and then there's the surroundings, which is pretty much everything else. Okay. So the universe is equal to the system plus the surroundings. System's what we're looking at, that's what we care about. The surrounding is everything else. Now, when we are looking at an equation like this and trying to figure out the internal energy change of the system, this is very useful for us because we have to consider the first law of thermodynamics. And the first law of thermodynamics states that energy is neither created nor destroyed. And this holds true even with regards to nuclear fission and things like that, where mass is destroyed and creates tremendous amounts of energy. Well, the truth is, physicists classify mass as a type of potential energy. So the matter that things are made of is we actually classify that now as a type of potential energy. And so the total amount of energy in the universe is always remains constant. It never changes. What does change is how that energy is distributed. How the energy is distributed and in what form. Because energy can be transformed into one form or another. So what this means is that since the total energy of the system, or rather since the total energy of the universe is constant, that means whatever the energy of the system is, whatever the change in energy of the system is going to be equal to the negative change in energy of the surroundings. So think of it like this. If the system gains energy, it gained it from the surroundings, so the surroundings lost that same amount of energy.
Is that why it's negative?
I'm sorry?
Is that why the negative or the minus?
Exactly. Because if the system gains energy, the surroundings loses energy, right? So that change in energy would be negative if this one is positive.
So they balance.
Exactly. If the system loses energy, then that means that the surrounding is gaining. So they're always going to be opposite. They're always going to be opposite, and that's what the negative sign here represents. Because the change in energy of the universe, as I've just mentioned, is always zero. Energy is neither created nor destroyed. And because of that, the change in energy of the system, it must be equal to the change in energy of the surroundings. Or the negative change in energy of the surroundings. Does that make sense? In terms of, we'll deal with this relationship a little bit later when we start talking about chemical reactions. But in terms of chemical reactions, we could say that the Q of reaction, so if the reaction loses heat, the surroundings will gain the heat. Or if the reaction gains the heat, the surroundings lose heat. So Q of reaction is equal to negative Q of surroundings. It's under the same basic principle. Does that make sense? Okay, cool. And the same could also be said of work. The work done by the reaction is equal to the negative work done on the surroundings. So, but we're not really quite as interested in work as we are in heat when it comes to chemistry. The work is really more of a physics thing. Alright, so negative or positive Q means the system absorbs heat, negative Q means the system releases heat. In the case of work, a positive W, positive work, means that the surroundings do work on the system. Whatever the work is done on, that's what gains the energy. Since the surroundings do work on the system, that means the surroundings lose the energy and the system gains it because work is done on the system. Think of it since this is primarily pressure volume work, think of a piston, okay? Let's say you have a piston that's completely airtight, okay? Here's your piston, here's the rod, and you have air in here, okay? Or think of even like a spring. You can think, maybe that's easier. Okay? If you're the surroundings, this is a system. If you're the surroundings and you push down on the spring, you've added energy to the spring, haven't you? Because if you let go of that spring, what happens?
It's going to rebound.
Yeah, it's going to shoot it up.
So
And that energy will be released.
That becomes kinetic energy from potential energy?
Exactly. The spring potential energy turns into kinetic energy. Exactly. And in the case of now, air kind of behaves the same way. It's not quite a spring, but what happens is if you compress air, the pressure increases, right?
Mm-hmm.
And then when you release that, the pressure will push it back out, right? So, when I push down on this piston, when I'm the surroundings and I do work on the system, I do pressure volume work on the system. I change the volume and increase the pressure. Does that make sense?
Mm-hmm.
So that's pressure volume work. I'm adding energy to the system by compressing it. That's positive work on the system. Negative work means that the system does work on the surroundings. This is on the system. This is on the surroundings. So if this is compressed and I release it, the air inside the piston pushes out against the surroundings. It doesn't work on the surroundings by pushing them out, right? And so that's the system doing work on the surroundings when it pushes out against the surroundings. Did that make sense? Cool. So, this is some just kind of basic definitions, a basic understanding of thermodynamics in a system. Now let's do a little bit of application on that. So in the first question, it says, in a thermodynamic study, a scientist focuses on the properties of a solution in an apparatus as illustrated below. The solution is continuously flowing into the apparatus at the top and out at the bottom, such that the amount of solution in the apparatus is constant with time. Is the solution in the apparatus a closed system? What do you think?
It's not a closed system.
No, it's not. Yeah, a closed system is a system that's cut off from the outside, that's separated from the surroundings. So, since a closed system is separated from the surroundings, nothing comes in or out. But in this case, you definitely have solution coming in, and you have other solutions coming out. So this is not a closed system. What could be done to make it a closed system?
Plug it out so that what you've put in now just is constant volume and it's recirculated.
Yes, connect the output tube to the input tube, so that the solution may still be circulating, but it's the same solution circulating. Or you could just simply plug both ends and just have the thing itself, right?
But if it's not moving, wouldn't it still be doing work? If it's just plugged, wouldn't it have to be recirculating to be doing something?
Well, it doesn't necessarily have to be doing work for it to be something you're studying, right?
Okay.
It depends on what you're studying. If you're studying a chemical reaction, you don't want stuff coming in and out.
No.
You just want that reaction to be measured within that isolated chamber. But good thoughts. Actually, I hadn't even thought about that, connecting the output solution to the input solution and making it a closed loop. I should have, but good job. Alright, is it okay if I race this? I probably should have asked before I started racing. Okay. So now let's take a look at number 2. It says, for the following processes, calculate the change in internal energy of the system and whether the process is endothermic or exothermic. So exothermic and endothermic refer only to Q. If Q is positive, if heat is absorbed, that's endothermic. Positive Q, endothermic. And negative Q is exothermic. Endo and exothermic have nothing to do with overall energy. They're only concerned with Q. They don't care about delta E. Alright, so let's take a look at A. A says, a balloon is heated by adding 900 joules of heat. It expands, doing 422 joules of work in the atmosphere. What is the delta E? So from my equation, I knew that delta E is equal to Q plus W, right? What is Q in this case?
900 joules.
900 joules. Positive or negative?
Positive.
Because you're
Positive.
putting it in?
Yeah, you're adding it, right? The balloon is the system, so it's a positive 900 joules. Now, what about the work? What's W? What's W?
422.
Positive or negative?
It's giving it to the surroundings, so it's negative?
It's negative. Very good. So negative 422 joules. So in this case, it's pushing out against the surroundings, so that is a negative W. And so this will end up being a positive 478 joules delta E. Positive 900 minus 422. Let's take a look at B, or B. So it says a 50 gram sample, and it is cooled from 30 degrees to 15 degrees, thereby losing approximately 3,140 joules of heat. So delta E is equal to Q plus W. What's the Q for this process?
The 3,140 joules?
Positive or negative?
Because it's negative, because it's cool.
Yeah, it's losing. Yeah, so negative 3,140 joules. So always ask yourself that question, is it positive or negative? Now,
Can you apply the thought that if it's cooling, it's always negative, and heating, it's always positive?
if you're talking about the particular substance that is being cooled or heated, yes. If you're talking about Q of reaction, that would actually kind of be turned on its head a little bit.
Okay.
We'll deal with that in a little bit. But your idea is not wrong. Now, what's the work done for B?
I was wondering is it the mass relationship?
There is no work. It's not pushing out, right? And it's not getting pushed in. It's just releasing heat. So there's no actual work done here. This is just negative 3140. Y'all are thinking too much. Too smart for your own good. Alright. Now it says a chemical reaction releases 8.65 kilojoules of heat and does no work on the surroundings. In this case, the system is the reaction. So what's delta E for this reaction? Or what's the Q? What's the Q?
Is it just zero because there's no change?
It releases.
Is there no change in heat?
There is, it's releasing.
So what's the Q then?
It'd be negative 8.65.
Negative 8.65. It's releasing heat, which is not absorbing it, it's releasing it. That means it's losing it.
Is it kilojoules?
Kilojoules, sorry. Negative 8.65 kilojoules. And what's W then?
0.
0. In this case, it's 0 joules again. So the overall delta E is negative 8.65 kilojoules.
So is Q always measured in joules?
Or kilojoules.
Okay.
And it could be measured in other units of heat, such as like BTUs or something like that. But that's pretty rare at this point. You can pretty much count on heat being measured in joules or kilojoules for chemistry. We don't deal with some of that other weird stuff. Maybe
So-
calories, but that's about it.
So is Q always like delta T? Change
sorry?
in temperature, Q always equal to delta T, change in temp?
No, that's a good point though. Temperature and heat are two very different things. So think of it this way. What has more heat? A swimming pool filled with 50 degree water, 50 degree Fahrenheit water? Or, like say, a Olympic-sized swimming pool filled with 50 degree water, or a hot tub filled with 100 degree water. Which has more heat?
Hot tub?
Swimming pool.
Why? Bigger volume?
Think of it this way. If you were going to freeze them, which would freeze first?
Probably the hot tub, smaller volume.
Exactly. There's less heat there. Now the heat is more concentrated, but there's less heat. Heat is a total measure of essentially the kinetic energy of particles in a system. Heat is the total measure of the kinetic energy of the particles in a system on a microscopic scale. Temperature is the average kinetic energy of particles in the system. The average kinetic energy. Temperature is a measure of. Temperature effectively measures the average kinetic energy of particles in a system. So you can think about, that's probably the best way to think about it. It's also one of the reasons why, like, for example, certain substances can hold more heat than other substances too. So like, for example, if you have boiling water, if you take 100 degrees Celsius boiling water and you drop a drop of that boiling water on your hand, it's going to hurt, right? It's going to burn. Probably get a little red mark. But if you have aluminum foil in a 450 degrees Fahrenheit oven, which is about, I don't know, about 250 maybe Celsius. So if you have 250 Celsius, literally more than twice the temperature of boiling water. But you have aluminum foil in 450 degrees Fahrenheit, or basically 250 Celsius oven, you can reach in and grab that aluminum foil with your bare hands and not get burned. Because the aluminum foil is not capable of holding very much heat. It's specific heat. The ability of its ability to hold heat is much lower than that of water. In the same amount of aluminum, it would take you about 5 times the aluminum to hold. It would be 5 times the aluminum to hold the same amount of heat as in the same amount of water.
So it's a function of the substance?
It's a function of the substance because it's dependent upon how tightly the molecules are attracted to one another and how effectively, or rather, how effectively it can store energy. The different ways it can store energy in the vibrational, rotational, and translational motion. Let's say vibrational, the molecules are shaking. Rotational, they're also rotating. And translational, they're moving. Okay? So, how effectively it can store energy in those 3 different forms. And aluminum just can't store energy anywhere near as effectively as water can.
Interesting.
So heat and temperature, completely different things. Completely different things. So that is why you have this different formulas that I'm going to actually show you now. We're going to actually be using. Actually, we'll use it in just a little bit for calculating heat. It's related to temperature, but it's not. It's more than just temperature. We have to consider other things as well. All right. So now, let's take a look at number 3. Scientists have done a lot of work on thermochemistry measuring how much heat is released and absorbed in different chemical reactions. And once they've studied a reaction, they actually will go ahead and identify, or they'll go ahead and record it in a standard table of what happens. This is one such reaction. Methanol, CH3OH plus H2, or rather, it's CH3OH, methanol gas, can decompose into carbon monoxide and hydrogen gas. And when it does, the delta H of this reaction is positive 90.7 kilojoules. Now I realize that we haven't really talked about what the heck delta H is. Well, it turns out that delta H, rather, H is Q plus PV. Okay? So, when we're looking at delta H, it's equal to Q plus pressure, rather, change in pressure times volume. Thank you. Oh yeah, okay, excuse me. So, most of the situations we deal with are constant pressure. And if the pressure is constant, then there's no delta P. Delta P is 0. So, we can think of delta H being approximately the same thing as P, or as Q. Because at constant pressure, delta H is equal to Q. Does that make sense?
Boyle's law?
No. What did you say?
There's like 3 gas laws about pressure and volume.
Yeah. And it's not quite related to that. It's a little bit different.
Okay.
Because this is due to the interplay with the temperature and pressure and volume. But basically, if we keep a constant pressure, most of our systems, most of the reactions that we study are all done at constant pressure. So if we're dealing with constant pressure, the delta H is equal to the Q. And then we can actually solve for delta H is based on that. Now there's a reason why we use delta H. The reason why delta H is important.
What is delta H exactly?
Delta H is referred to as enthalpy. And enthalpy is a state function. That's one of the reasons why it's so useful. Because when we looked at delta E is equal to Q plus W, delta E, or change in internal energy, is also a state function. Now, what the heck is a state function? Well, a state function is a function that is dependent only upon the initial and final states of the system, or the state of the system. And when it's change in when it's change in E and change in H, it's only dependent upon the initial and final states of the system. So change in temperature is a state function, right? Because it doesn't matter if you heated it up and then cooled it down, the overall change is going to be the final temperature minus the initial. Same thing with delta H. It doesn't matter where you start, or it doesn't matter how you get there, it matters where you start and where you end. So, for example, by analogy, another state function is displacement. Displacement is the difference between where you start and where you end. So if I walked out, jumped on a plane, flew around the entire world, came back, and by some miracle you were still here, you would have, my displacement would have been 0. Because I had literally not changed my position from the point when I left to the point when I got back. However, and so that would be a state function. It's only dependent upon my initial state and my final state. However, if we talked about the money I used, or if we talked, like the money I spent would not be a state function, because if I just went home and slept for a few days and came back, I would have spent far less money than if I traveled around the world, right? Distance would also not be a state function, because if I simply went home, slept for a few days, come back, that would be a very short distance I traveled, just several miles home, several miles back. But if I went around the world, I'd be traveling thousands and thousands of miles. So distance is not a state function. But a state function is something that only depends upon the initial state and the final state.
So if the beginning and the ending states are the same, there is no change?
Exactly. Now, Q is not a state function, and neither is W. So this is not a state function. This is what's called a path function. Like distance, these are called like distance and the amount of money I spent, these are called path functions. And the reason they're called path function is because they depend upon the path you take. Now, for example, there's a lot of different ways that I could get a particular change in energy. I could absorb a bunch of heat, or I could have a lot of work done on me, right? So the value of Q and W depend upon the particular path that I take to get to a particular ending. But the delta E is not dependent. It's just dependent on the initial energy state and the final energy state.
So going back to your analogy about travel, if you drove versus walked, there would be a difference, and that
Exactly.
would be a path that you took to get to the same spot, which would be the state.
So the displacement, yeah, so the displacement would be a state function, because whether you drove versus walked. But the amount of energy you used would be, like for example, if you drove in a car, the amount of heat released would be a lot larger, right? But the amount of, but not necessarily the amount of work, because there's a lot of, and when you use a car, it's very inefficient, and there's a tremendous amount of heat that's released from the combustion engine. Whereas if you walked, your body is a little bit more efficient in using its energy than a car would, and so you'd release less heat.
Okay.
You do a lot more work if you walked, right? Because there's a lot of more extraneous movement of the arms and legs. So, anyway, does that make sense? State function, path function? No, because it's a lot easier to measure it's a lot easier to measure delta H. We want to deal with state functions, because that allows us to compare various different reactions and figure out how much energy how much the enthalpy would change if we combine several different reactions together. But we can do them at constant pressure, so they're easier to measure. And because we can measure heat more effectively than we can measure enthalpy directly. But if it's a constant pressure, then they're the same thing. Does that make sense? It's basically, by using a constant pressure system, we simplify this into this. And it makes it a lot easier for us to measure and calculate delta H. Alright, so let's take a look at number 3. We have the reaction equation, we have the delta H, and we're going to go ahead and need to recognize that this delta H here refers to the molar amounts of each of these. So when I say the delta H of this reaction is 90.7 kilojoules, I mean that 90.7 kilojoules, since it's positive, that is it absorbed or released?
Absorbed.
It's absorbed. So 90.7 kilojoules are absorbed when 1 mole of CH3OH reacts to form 1 mole of CO2 and 2 moles of H2. So this amount refers to the coefficient number of moles of each of these substances in this reaction. So it says calculate the amount of heat transferred when 45 grams of CH3OH is decomposed. So I can start with 45.0 grams of CH3OH. But since I know that this heat refers to the moles of each of these, I can go ahead, I'm going to need to go ahead and convert the grams to moles first, before I do anything else. And so if I'm converting this, what unit has to come down here?
Grams of CH3OH.
Grams of CH3OH. And what unit's going to come up here?
Moles of CH3OH.
Moles of CH3OH. Very good. So 1 mole is equal to the molar mass. Well, carbon's 12, oxygen's 16 from the periodic table, and hydrogen's 1, right? So 12 plus 16, 28, plus 4, 32. So I get 32.045 if I include 4 decimal places. And that gives me moles. Now here's the really cool thing. Now since I see this positive delta H is 90.7 kilojoules, if I wanted to, I could add that to my equation. And since it's being absorbed, is heat a reactant or a product?
Reactant?
It's a reactant. Because if heat is produced, if it's released, it's a product. But if it's absorbed, that means it's a reactant. So what I can do here is I can use that relationship and I can relate CH3OH to the heat. And so moles of CH3OH, 1 mole is going to give me 90.7 kilojoules of heat. Does that make sense? And so then I can just multiply by the top and divide by the bottom. And if I do, what do I get?
I got 127.34.
100 and what?
127.34.
That sounds good, 127. Now it's 3 sig figs here, so my answer is just going to have 127 kilojoules. So that's part B. Now part C says for a given sample of CH3OH, the enthalpy change on a reaction is 18.5 kilojoules. How many grams of hydrogen gas are produced? So in this case, oh sorry, this is actually B. I'm getting my letters mixed up. C. Okay. So 18.5 kilojoules is what we start with. In this case, it's kind of, for part C, it's actually kind of the reverse of part A. Here we started with grams and converted to how many kilojoules would be released. Here we measured the amount of kilojoules released and we have to figure how many grams got reacted. So, what unit's going to come at the bottom here?
Kilojoules.
Kilojoules. What unit's going to go on top? Moles of what? Hydrogen gas. I'm interested in hydrogen gas, right? That's what I'm trying to find. I'm trying to find the grams of hydrogen. Now, how many moles of hydrogen corresponds to how many kilojoules?
2.
2 moles of hydrogen, very good. And how many kilojoules does that correspond to?
90.7.
90.7. And now that I have moles of hydrogen, I can convert to
Grams.
grams of hydrogen. So moles of H2 comes on the bottom and grams of hydrogen comes on top. And so 1 mole of hydrogen is equal to 2.02 grams of hydrogen. And now I can simply multiply everything on top, divide by everything on bottom, and I will get something. What is my something?
.824.
Yeah, 0.824. And once again, 3 sig figs, so my answer is going to have 3. 0.824 grams of H2 gas, hydrogen gas. Excellent. Well done, well done. Now for the last one, it says, what is the value of delta H for the reverse of the above reaction? So if I flip this reaction, because, as you may or may not know, reactions actually can go both ways. What?
Oh.
So, you could actually have 2H2 gas plus CO gas going to form CH3OH. And if that was the case, where would the 90.7 kilojoules be?
On the other end.
Yeah, it'd be on the product side. You'd have 90.7 kilojoules would be on the product side, which means they would be produced. Which means that the delta H here would be what? Negative. Negative 90.7. When you flip a reaction, you flip the sign of delta H. And that makes sense, right? Because if you're going this way and it's absorbed, if you go the opposite way, it's released. And therefore, that would flip the sign of delta H. Cool. So now, it says, how many kilojoules of heat are released when 27 grams of carbon monoxide reacts completely with H2? So here, I'll take my 27 grams of carbon monoxide, D, 27.0 grams of CO, and I will set up my conversion factor. What goes on bottom? Grams of CO. What goes on top? Moles of CO, because moles are what make everything possible. Not really, but you know, I can do a lot with them. Now, the molar mass is 28.01 grams per mole, 16 plus 12. Now that we have moles of CO, I can convert to kilojoules. Moles of CO converts to 90.7 kilojoules. Now here's the thing. Is this positive or negative? Negative, because it's being released, right? Now here's the deal though. If I multiply the top, divide by the bottom, what do I get?
87.4.
Negative 87.4 kilojoules. Now here's the deal. Here's the deal. Now there's a deal. Let's make a deal. It asks us how many kilojoules of heat are released. So is this my answer?
We need to subtract it? Or,
This is one of my least favorite parts about thermochemistry. Semantics. Basically, when it says how many kilojoules of heat are released, you can't release a negative amount of heat, right? Just like you can't talk to a negative a number of people, like, right? I talked to negative 4 people today. That doesn't work, right? You can't have negative 3 chairs at a table. So you can't have a negative amount of heat. So when it says how much heat is released, then the negative here indicates the enthalpy change. This is the enthalpy change, the change in heat of the system. Okay? The change in heat of the reaction. This is the change in heat of the reaction. And you can have a negative change, like you can have a negative change in temperature, right? If the temperature goes down, it gets cooler, there's a negative change in temperature. But you can't have a negative amount of heat. So you have to watch the wording. If it asks you for the Q, if it asks you for delta H, change in enthalpy, if it asks you for what is the heat change or what is the change in heat, the answer would be negative 87.4. But since it asks you not for the change, but rather for the heat released, you have to give your answer as a positive. Like I said, it's kind of a stupid semantics thing, but that's how it has to work, unfortunately. Does that make sense?
So we would just put 87.4, no negative at all?
Exactly. So the answer is actually positive 87.4 kilojoules released. Behold its glory.
And that's all just like assumed, there's no way to indicate that it was negative prior?
Well, but since it's asking for the amount of heat released, you'd say, well, 87.4 kilojoules is released. But if it, like I said, if it asked you for what is the value of Q for this reaction, you would say negative 87.4.
Okay.
If it said what is the delta H for this reaction, for 27 grams reacting, then you would say negative 87.4. But it just depends on if they're asking, are they asking for heat or are they asking for change in heat? And Q and delta H both refer to a change. But if it just says heat released, it's always going to be positive.
Okay.
I mean, in a sense, it's kind of important because it forces you to be precise with your language.
Mm-hmm.
It forces you to be precise with your thinking, too. Because imprecise thinking can actually be very, very dangerous for a scientist. Because imprecise thinking leads to erroneous conclusions. And we actually, unfortunately, do see signs of that all the time. So, next. Consider the decomposition of liquid benzene C6H6 to gaseous acetylene C2H2. So C6H6. Oh, not equilibrium, sorry. My bad. You're not ready for that. That's Gen Chem 2 stuff. What am I thinking? Alright, is equal to 3, or it's going to form 3 C2H2 acetylenes. So here is the deal. Yes, there's always a deal. I need to stop saying that. Okay. Basically, what we're dealing with here is it wants to know what is the enthalpy for the reverse reaction. It actually tells us the enthalpy of the forward reaction. The enthalpy of the forward reaction is positive 630 kilojoules. So the enthalpy of the reverse reaction would be?
Negative 630?
Exactly, exactly. And likewise, a positive 630 kilojoules means that heat is a
Reactant.
reactant. 630 kilojoules is a reactant. If I flip this reaction equation around, I would have 3C2H2 going to form C6H6, and this is actually a liquid, and this is a gas, and this will be important for reasons you will soon find out. the delta H, and then of course this is plus 630 kilojoules. And because it's a product on this side, that means heat is being released, which means the delta H for this guy, for this equation, is negative 630 kilojoules. And I don't know why I don't start it a little further over here and not have to run off the edge. Okay, so now, basically, it says, what is the delta H for the formation of 1 mole of acetylene? Now here is an interesting thing. This is 1 mole of acetylene, right? 1 mole of, well, this is acetylene, the C2H3. If I want to figure out what is the delta H for the formation of 1 mole, what do I have to do with this equation?
Divide all of it by 3.
Divide all of it by 3. And if I do that, I end up dividing this by 3 as well, don't I? So this becomes 210 kilojoules. And then plus, now dividing this by 3, this becomes 1/3 C6H6. And this becomes C2H2. There's only one of them. And then, of course, the delta H then for this, since I had to multiply this by 1/3, and it's still on the reactant side, it's going to be positive 210 kilojoules. Does that make sense?
I just have to copy this and I have to make notes.
Now, you might be like, that's not valid. You can't have a 1/3 in a balanced chemical equation. What is this trash? Be like, you're right. Under normal circumstances, we could not have a balanced equation like this. But in thermochemistry, we can do things we're not supposed to. Because this delta H, remember, is kilojoules, right? And while you cannot have 1/3 of a molecule of benzene, you can have 1/3 of a mole, right? And since this is kilojoules per the molar amounts of each of these, that's why we kind of get a little bit of an exception when it comes to thermochemistry. If this question had said, what is the enthalpy change, or what is the change in enthalpy for the formation of 1 mole of benzene, what would your answer have been?
Times that with 3.
Yeah, negative 630. Because if it's for the formation of 1 mole of benzene, well, if you're forming 1 mole of benzene, that means benzene must be a product, right? So you gotta watch for how they word these reactions. Sometimes they'll give you a reaction going one way, but then they'll ask you a question that implies that the reaction is going the opposite way. And if that's the case, you have to flip the delta H. Does that make sense?
Yeah.
Okay. Now it says, which is more likely to be thermodynamically favored? The forward reaction or the reverse reaction? What do you think?
A forward reaction?
So,
It's going to give off.
is it going to be easier to absorb? Is this reaction going to be more likely to happen where it absorbs 630 kilojoules of heat, or where it releases 630 kilojoules of heat?
Would it be released?
Release? And if you think about it this way, is it easier to go from low energy to high energy, or from high energy to low energy? High to low. So like, for example, think about it like, and it's a very apt analogy, think about it like going up a hill or going down a hill. If I'm going up a hill, my energy is increasing, right? But it's hard, because I have to really work at it. I have to input some energy to get up to that high energy state at the top of the hill. However, if I'm going down the hill, it's so much easier. I'm releasing, or I'm losing energy because I'm losing potential energy going down the hill, but that energy that I'm losing is actually making it easier for me to go down the hill. It's very natural. I can roll down the hill. In fact, if the hill is smooth enough, I could just sit down on my behind and go right down the hill, you know? So I wouldn't even have to do any work at all. So it's always easier to go from high energy to low energy than it is to go from low to high. So what it says is that thermodynamically favored, negative delta H's are always going to be thermodynamically favored because you're going from a high energy state to a low energy state. It's kind of like what I said earlier when we talked about the energy of the universe being constant. The energy of the system is equal to the negative energy of the surroundings. For it to release this much energy, that means this was a high energy reactant going to a low energy product. What happens to the rest of the energy? It's released to the surroundings. Now, we can look at D. It says if C6H6 gas was consumed instead of C6H6 liquid, would delta H increase, decrease, or stay the same? So in other words, instead of the liquid here, if I had C6H6 gas to 3C2H2, seriously, I cannot draw today. Okay. 2. Then what would happen to the magnitude of delta H? Would this increase or decrease? What do you think?
Wouldn't it actually stay the same?
Well, let me ask you, because delta H is the change in heat energy, right? Sure, the change in enthalpy. So,
Well, then it would stay.
does this have any? This has the same. This clearly has the same energy as this, right? Because they're the same thing. So the product is the same. Delta H is the H of the products minus the H of reactants.
So is the reactant any different if it's in a different state?
So let's think about that. Is steam higher energy than water?
Yes.
Yeah. Gas is this gas higher energy or lower energy than the liquid?
It's probably higher, but does it depend on the substance as well?
I mean, there is a certain aspect to that, but in this case, you're not changing the substance from here to here. In the reactant, it's the same substance. You're just one is in the gas phase, the other's in the liquid phase. And the gas phase, the particles inherently have more energy. They're moving faster. Like in the liquid phase, the forces of attraction are not overcome, so they're still pretty close to each other, and they can't really move that much. But in the gas phase, they can move freely, and they move quick. They're free from any attractive forces between particles. So this is definitely higher energy. And if this is higher energy, so it's this minus this, so if I'm subtracting a larger number, what's that going to do to the delta H here? It's going to decrease it. It's going to make it more negative or less positive. In this case, it's still pretty darn positive here. So it's, in all likelihood, it's going to be less than 630 kilojoules. So maybe instead of 630 kilojoules, it would only take, say, 578 kilojoules. And that's just a number I made up. I don't know if that's actually true. I like to make things up. So, it'll definitely take less energy to get this to here. It's like going up the hill. If you're already halfway up the hill, it's going to be easier than if you're at the bottom of the hill, right? And this is actually why steam burns are so dangerous. Because if you get burned by steam versus boiling water, and boiling water will hurt. And that'll hurt bad, it can burn you pretty bad. But a steam burn is much worse. Because a steam burn, all of the energy that's in the gas phase, it loses as it condenses onto your skin. And then once it's condensed, it's still at 100 degrees Celsius. to put it this way, and you'll learn about this in a little bit more later, effectively, in solid, so, as you add heat, now here's the temperature. As you add heat to a substance, it will the solid will warm up until it reaches the melting point, at which point it will melt. While it's melting, it does not change temperature. The temperature stays constant until all of it is melted. Once it's all melted, then it starts increasing temperature again. Once it's all completely, or once it reaches the boiling point, then it will start boiling. But while it's boiling, the temperature is constant. It's 100 degrees Celsius until it becomes a gas, all of it, at which point it can start increasing temperature again. So even if you just go from 100 degree, even if you just go from 100 degrees steam to 100 degree water, that's more energy released than it takes to go from 100 degree water to freezing water. That's a lot of energy. Very dangerous. So, that's why even if these were at the same temperature, even if this was 25 degrees Celsius and this was 25 degrees Celsius, this would still be much higher energy. Now let's look at one last thing before we call it quits, and the rest of this will have to wait until part 2 of thermochemistry next week, to be continued. Alright, we are going to look at calorimetry. Calorimetry is the process of measuring heat changes in a reaction. Okay? Essentially, in calorimetry, the Q of the reaction, or the Q of the process, is equal to the negative Q of the calorimeter. The Q of the process is equal to the negative Q of the reaction, or Q of the process is equal to the negative Q of the calorimeter. And this is based upon that notion of the energy of the universe remaining constant. Now there's several different ways to measure, several different types of calorimeters you can have. There's the constant, or there's what's known as the bomb calorimeter. And a bomb calorimeter is basically kind of like a cylindrical device, okay? And in this cylindrical device, you have an inner reaction chamber. This inner reaction chamber is entirely contained and airtight, and usually there's some sort of a wire or spark plug inside, igniter, that can set the sample inside on fire. Here's my little sparks. Spark, 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 spark. Fire. Okay. And then there's typically some sort of substance inside that's catching on fire. And you burn it in the calorimeter. Okay? In addition, there's usually some sort of fluid that is sealed inside the calorimeter, so that when, like maybe water or something, so that when this sample is ignited, all of the heat that's released in here gets absorbed by the liquid. All of the heat that's in here gets absorbed by the liquid. And lastly, you have a thermometer. A thermometer in here, little red line here. Can't draw with the dollar. Okay. And you have a thermometer there, and basically that measures the temperature change inside the fluid. Okay? And this is, of course, sealed on top, sealed and insulated on top, sealed and insulated so that no heat gets out to the, or as little heat as possible at least, gets to the surrounding environment. And usually there's also additional insulation on the outside and bottom of this thing so that there's no heat transfer or as little as possible to the surroundings, like maybe some styrofoam or a vacuum. Because for heat to transfer, it needs to be transferred particle to particle. So if you have an evacuated chamber, if you had an this wouldn't be stuff you're going over, sorry. If you have an evacuated chamber, where there's literally no air in here, it's not able to transfer heat from inside to outside. But you could also use something like styrofoam, which is really, really bad at conducting heat. And so that will also be a pretty good insulator as well. Alright, basically then, here's your bomb calorimeter. And for a bomb calorimeter, the Q of the cal can be measured based on the heat capacity of the calorimeter. Now the heat capacity of the calorimeter is usually, the symbol for that is C-cal times delta T. So C-cal is the heat capacity of the calorimeter, delta T is the change in temperature. And usually with these bomb calorimeters, they're measured in the lab, their heat capacity, so you know exactly how much energy it takes to increase the temperature of this whole thing by 1 degree Celsius. Like, it'll give you like a 12 kilojoules per degree Celsius. So it takes 12 kilojoules to raise the temperature of this whole thing by 1 degree. So you can also have what's known as a simple coffee cup calorimeter. And this is basically where you just have a couple styrofoam cups.
Oh, we do that.
I've already done it in 1405.
Yeah. So you have a couple styrofoam cups, and it's just coffee cup calorimeter. Now it's not as obviously sealed like this, but this is constant pressure, whereas this is not. So this, I mean, there's plus and minuses to both of them. This is also less expensive. But usually you just stick your thermometer in here. Okay. Stick your thermometer in there, and then you have usually some sort of a solution. And then you have some sort of reaction that takes place in there, and you measure the change in heat.
Ice melting.
Yeah. And in this case, then there's actually two things you have to consider: the heat capacity of the calorimeter and the heat change of the solution. In the case of the heat change of the solution, or if you have a solid block of metal and you're trying to figure out how much heat is absorbed or released by the metal, then you use the equation, the Q of the solution, or Q of the metal, is equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. Remember how we talked about earlier how, like, for example, water is much more efficient at holding heat than, say, aluminum? Well, that's what the specific heat tells us. It tells us how efficient something is at holding heat, or like how effectively it holds heat. So if C is high, then that means the substance is capable of holding a lot of heat per degree Celsius. If the C is low, like a metal or aluminum, then that means it's very inefficient, it's very poor at holding heat, can only hold a little bit. You add just a little bit of heat, and then it like jacks the temperature up. Does that make sense? So, and this, like I said, usually in the case of calorimetry, we do use this in terms of solution. So the Q of solution is equal to MC delta T. But this can also refer to any single substance, any metal or object of any kind that's only composed of one type of thing. If you have a complex object that's composed of many different parts, you're going to use heat capacity of the calorimeter or something like that. You're going to use its heat capacity. But if it's only one type of substance, it's all gold, or it's all aluminum, or it's all water, then you can use this one. There's also another equation you can use in the case that it gives you moles of a substance. It's basically the same thing as this, but it refers to molar heat capacity if you're given molar heat capacity. So if you have C molar, which is the molar heat capacity, it's going to be the moles times the molar heat capacity times the change in temperature. But like I said, you're probably not going to deal with that too much. You may see it once in a while. Generally speaking, it's going to be one of these that you're going to use. Does that make sense? I know, it'll make more sense when we practice it. Alright, so for number 5, it says a 1.8 gram sample of phenol was burned in a bomb calorimeter whose total heat capacity is 11.66 kilojoules per degree Celsius. It says the temperature of a calorimeter plus content is increased from 21.36 degrees to 26.37 degrees. Write a balanced chemical equation for the bomb calorimeter reaction. So in this case, it's a combustion reaction, right? Because you have phenol that's burned, right? So phenol, it tells us, is C6H5OH. And if it's a combustion reaction, that means it's reacting with what?
Carbon dioxide, or oxygen.
Oxygen.
To produce carbon dioxide and water.
So this is phenol. And it says, we don't know if it's gas or a liquid, we'll just say it's a liquid. And it produces carbon dioxide, right? And water, right? Now in terms of delta H, it actually makes a difference which one we use. It actually makes a difference if we use gaseous water or liquid water. But, yeah, because remember, the gases are higher energy, right? So if you change the phase, you'll change the delta H.
So would it not just be steam at that point?
It would be steam. It would be steam. Now, because it's trapped in the bomb calorimeter, though, we're going to assume that it eventually condenses inside the bomb calorimeter because the temperature, the final temperature of everything only reaches 26.37 degrees, right? So it initially gets formed as a gas, but it'll condense. At 26 degrees Celsius, that's about 78, 79, almost 80 degrees. That's 80 degrees Fahrenheit, that's not enough to boil water, right? That's like the temperature it's going to be this Sunday. Right? So now what we're going to go ahead and do is we're going to go ahead and calculate the Q for the calorimeter. Because it wants to know, oh actually before we can do that we have to balance this equation, right?
Yeah, don't we have to balance it?
Alright, so let's balance it. Tell me what to do. You guys are the masters now.
Would we start with maybe the carbon dioxide adding 6 in front of it?
Yeah, let's balance carbon, right? I have 6 C's on both sides, good. Now what do we want to balance next?
Probably the water, because that's where we're going to need to increase the oxygen, because we've got 12 oxygens,
Well,
13
remember-
oxygens, right?
We want to balance element by element. So we're not balancing water, we're balancing
Oxygen.
hydrogen.
Oh, okay.
And the reason we want to balance hydrogen before oxygen is because oxygen is what?
Single one by itself?
Well, oxygen is present in every single compound. That makes it very difficult for us to balance. Because we don't know if we have to adjust this and this, or just this, or this and this, or just this. We don't want to try to mess with oxygen until the very end. When everything else is balanced, oxygen should be able to be pretty easy. But for now, let's leave it alone. Because hydrogen is going to be much easier to balance. It only is present in 2 compounds, here and here.
Okay, so we've got 6 hydrogen on the left, and we've got 2 on that side, so if we change to a 3 coefficient.
Good. And so now we have hydrogen balanced. Now we can balance oxygen. So let's first figure out how many oxygens we have on this side.
12 plus 3 is 15.
So you have 15 total oxygens over here. How many oxygens do we have on this side? 3, right? Now here's the deal. It may look like, oh, we can just multiply by 5, but I can't really do that because oxygen is present in 2 places here, right? Furthermore, if I change this one
change.
I'm going to have to change these, and that'll mess this up, right? So let's see if we can balance oxygen by just changing this. This gives us how many oxygens?
1.
1. So, if that's the case, if this gives me 1, I need how many more to get 15?
14,
14.
which would be 7.
There you go. Good deal. Alright, so now we can proceed. It says, write a balanced chemical equation for the bomb calorimeter reaction. Then it says, what is the heat of combustion per gram of phenol? So to get the heat of combustion, then we're going to have to take the Q of this reaction, the Q of the reaction, and divide it by the grams, or the mass, of phenol. The heat of combustion is the Q of the reaction divided by the grams of phenol. This is the heat of combustion. Now, I don't have any information that can solve directly for Q of reaction. However, I do know that Q of reaction is equal to the negative Q of the calorimeter, right? So what I can do here, let's pull up some fancy colors. Fancy colors. Okay. Q of reaction is equal to the negative Q of the calorimeter. And the Q of the calorimeter is this P capacity of the calorimeter times the delta T. Now the reason I know that I want to use the heat capacity of the calorimeter versus the heat of the solution is because of Y. What in the problem tells me I need to use the calorimeter one versus the solution one?
The bomb.
Yeah, it says you have a bomb calorimeter, and furthermore, it says the heat capacity of the calorimeter. So we're dealing with heat capacity here. So now I'll just go ahead and plug in my numbers. The heat capacity of the calorimeter is given as 11.66 kilojoules per degree Celsius. And then, actually I'll use brackets so it looks nicer. And then I'm going to multiply that times the change in temperature, which is the final temperature, 26.37 degrees Celsius, minus the initial temperature, 21.36 degrees Celsius. And from there, I can simply calculate what that is. And what is that? Yeah. 58.46.
42.
42. That's what I said. Now, I will say this. We actually only have 3 sig figs. And the reason we only have 3 sig figs is when you subtract these two, you get the number 5.01. And even though these look like it have 4 sig figs here, when you subtract them, you end up only having 3 because when you're subtracting, it's how many decimal places it has, right? So that's going to mean 58.4 kilojoules. Now, I can take my 58.4 kilojoules, which is my Q of reaction. This is my Q of, actually I forgot to add a negative sign in front. Q of reaction, right? It's negative because the Q of the calorimeter would be positive 58.4. But because we're looking for Q of reaction, that becomes negative 58.4. Because whatever the reaction lost is what the calorimeter gained, right?
Yeah.
See, we're measuring the Q of reaction. We can't measure it directly, so we have to measure it based on what happens to the surroundings. This bomb calorimeter is our own isolated little universe. Here is my little system. The system is this. The system is the chemical substance. The surroundings is everything else around it. Okay? The system loses energy because the chemical substance is converted into a less energetic chemical substance. But the surroundings, the calorimeter, increased heat from 21.36 to 26.37.
As measured by the thermometer.
Yeah. So because this got warmer, that means energy was released from the system. The energy was released from the reaction. The Q of the calorimeter is positive, but the Q of reaction is negative. The calorimeter gained because the reaction lost.
That's why the reaction is negative?
That's why the Q of reaction is negative. Because the surroundings gained energy. Now, if this had gotten colder, that means the reaction would have absorbed the energy, which means the Q of reaction would have been positive. But since this got warmer, that means the reaction released energy, which means the Q of reaction is negative.
That's how a refrigerator works. It absorbs heat.
Yes, exactly. The condenser,
refrigerant
it
in
absorbs.
the back, heat and gives it off.
Yeah, it absorbs heat inside the refrigerator
Yes.
and then releases that heat outside the
Through
refrigerator.
the coils in the back.
Exactly. Exactly.
I do actually remember something from all the stuff my grandfather taught me years ago that makes sense now in relation to this.
Yeah. Very true. Okay, so now all I have to do to get the heat of combustion is to take my Q of reaction divided by the Q grams of phenol. So I'll take, I feel like I got too much going on here. I'm going to erase this up here. Wow. Okay. Then I'll take my Q of reaction, which is negative 58.4 kilojoules, divided by the grams, which is 1.800, right? Grams of phenol. And that's my heat of combustion. Heat of combustion. Aha! That's almost looks like an equal sign. There we go. Better. So that will give you some number, I'm not sure what it is, probably in the 30s. What's it, Jade?
32.44. And because, so no, sig
Okay.
figs is 34. There's only 3 sig figs because the top is 3 sig figs.
Exactly. So this is the heat of combustion per gram. Now if we want to do a heat of combustion per mole, all we have to do is take our heat of combustion per gram. Well, we could do it two ways, honestly. Perhaps the easier way to think of it would just simply be to take the 1.88 grams of C6H5OH and convert that from grams, C6H5OH, to moles of C6H5OH. Bam. And 1 mole is equal to the molar mass of this, which, go ahead and calculate that, and I'll see if I can do it in my head. Alright. Alright, so now you just 1.8 divided by 94.12, and if you do that, you will get
A number.
a number. A fancy number. What looks like this? 0.01912. There, that's right. That's moles of C6H5OH.
Would we put that in scientific notation to get sig figs correct?
Nah.
Okay.
That is the correct sig figs actually, that's 4. I don't use scientific notation unless I have to. So now I'm going to go ahead and take my same negative 58.1 or 0.4 kilojoules and then I'm going to divide it by my moles, 0.01912 moles, and that's going to give me my molar heat of combustion.
I got negative 3054 point, or just 3054 or 5?
Negative 3050.
5.
Negative 3054, because only 3 sig figs, right?
Oh, right, yeah.
Bam. Molar heat of combustion. That's a lot of heat. Hydrocarbons release a tremendous amount of heat when burned, which is why we use them for energy. Yay! Behold the greatness. There you go. So, we're going to stop there for now, because next time we're going to get into what's known as Hess's Law, which is going to be lots of fun. And then we'll do some other crazy stuff as well. Maybe some more calorimetry. Cool. Thermochemistry is one of the most difficult chapters because it is because there are so many facets to it. There's so many different concepts that you have to kind of think about. And we'll cover a good half of those concepts today. We'll cover the next half next time. And sorry if we kept you a little bit long. I know it's an hour and a half.
No, it's okay.
Thank you for coming.